school, I had to take like a 5 o'clock on Colts. It's very cool. On Colts. Colts another one of religion. So it's like half the semester is like world religion, the other half is Colts. It's like Colts, that crazy movie. Yeah, but you know, Brigham Young, who watched the movie like September Dawn, where he like before basketball. Have you ever seen that one? You know, like all about this thing. It just reminds me of chickens every time. So I always think of like the big KKK. Just in that. Oh, if you mentioned it, we were in KKK.
The Chem 2 classes had their midterm last week, and it was ugly. So it was so ugly, not only am I going to scold them tomorrow, but I'm going to scold you today. Don't get yourself in the situation where you start making a lot of mistakes on things you've gotten right previously. All right, when you get your exams back, you need to be correcting your mistakes while it's fresh on your mind and reviewing those things. All right? You are digging yourselves a very deep hole if you don't repair your errors and go back and review periodically. And I think that's kind of what happened with them. Once test 1 was done, they put it away and they never thought about it again until midterm, when they realized they didn't even remember what the symbols meant, much less the formulas and how to calculate with them. All right? It wasn't bad, it was embarrassingly bad. All right? So don't be like them. And you've gotten your exams back from previous parts. We don't have a midterm, but you do have a final. And that final is comprehensive over the whole semester. And you don't want to be in the situation they're in right now, simply due to lack of preparation and timely preparation. All right? You don't want to wait till the end to start your review, because then you'll be too rusty on too many things. You should be taking those exams as you get them, prepare things and move on, and that way it builds, and that way it never gets rusty. Go ahead.
What would you recommend, like, people taking into, like, over the break?
As far as, I would, nothing, as far as Chem 2, there, I wouldn't do anything as far as new material, but you'd want to go back and you'd want to look over charges, you'd want to look over naming system, you'd want to look over ionization, dissociation, and neutralization reactions, and you'd want to look over mole relationships. And if you review those and you come in good on those, then you're off to an extremely good start. Because those are the parts that don't go away. All right, I feel better now. I will let it go. The 3 reaction types we're going over today are all acid, well, no, not strictly acid-base related, but primarily acid-base related. And you've talked about acids and bases before, particularly, I guess, just in terms of nomenclature. Dissociation is a reaction that happens when you put an ionic compound into water. So it's when an ionic compound dissolves in water. So if this is our water, and this is our ionic compound, positive and negative ions attached in a crystal, you put that into the solution and they separate. Water is behaving as a solvent, meaning that it's dissolving the other material. And the only thing that happens is separation of the existing ions. Because if we start with these cations and anions together, you put them in the water, you still have those same cations and anions, but now they're apart. Then you haven't really changed the identity of anybody. If this were sodium chloride, as the reaction says, sodium chloride as a solid becomes sodium ions and chloride ions as separate particles. The difference is they're no longer attached to each other, but you end with exactly the same ions as you start with. That's the key. And when you look at that formula NaCl, you don't see any plus or minus charges, but they're there because this is sodium is a metal, chloride's a nonmetal. You think about their charges. These are already Na plus and Cl minus. Before it ever hits the water, it's already Na plus and Cl minus. And all the water does is floats them apart. Separation of the ions that already exist. So the dissociation of aluminum nitrate, what this is made of is 1 aluminum and 3 nitrates. So guess what your products are?
Aluminum, nitrogen,
1 aluminum and 3 nitrates. The nitrate ion. You're not separating atoms, you're separating ions. And that nitrate is a polyatomic ion. The nitrogen and the oxygen are both nonmetals, and so that nitrogen and oxygen are held together covalently. That was a polyatomic ion like from Lewis structures, right? Where we drew that one out, I think. But for the most part, with dissociation, the ionic bonds break and the covalent bonds don't, and that's why that nitrate ion remains intact. You start with 1 aluminum ion and 3 nitrate ions, you end with 1 aluminum ion and 3 nitrate ions. They're just not bound together anymore. Go ahead and do the next 2. And make sure you show the charges on your products. On the previous one, it was not Al and NO3, it was Al as a +3 ion and NO3 as a -1 ion. Dissociation will always give you charged products. And that's a critical part of the reaction. Make sure you show that charge. Is this what you got for ammonium bromide? This is what you got on the calcium hydroxide. Make sure you're showing the charges. All right. Now before we do the last one, we've got a little bit of definition and distinction here to make. Over on the right-hand board, I've written up the definition for a base. Acids and bases are considered opposites. Acids are corrosive, they react by releasing hydrogen. Bases essentially neutralize acid. So they're the opposite, the counterpart to an acid. The definition of a base that we're going to use anyway is it's a material that creates hydroxide, OH-, as an independent ion in solution. Any substance that is capable of producing OH- as an independent particle, that's a base. Which means this is a base. Because one of our products just happened to be OH-, correct? Now, you can look at that and see the OH in the formula. But just having OH in the formula does not make it a base. The definition is not something with OH in the formula. It's something that releases or produces OH-. And since those hydroxides come loose, that's what makes it a base. And there's different degrees of strength as far as some bases are more effective than others. The strong bases are ones that you need to memorize. This is the hydroxides of lithium and all the elements below it on the periodic table. And the hydroxides of calcium and all the elements below it. Those particular metal hydroxide compounds are considered strong bases because when placed in water, they dissociate 100%. Meaning, if this is our beaker and this is our water, when you put calcium hydroxide in there, every single particle that you place in is going to separate into ions. There will be absolutely zero CaOH2 units that are floating around intact. Every single one separates as complete conversion into products, one of those products being hydroxide. Bases produce hydroxide, strong bases produce a lot of hydroxide. They give you 100% dissociation. And weak bases don't. The weak bases happen significantly less, and by significant I mean for the weak bases, which is everybody else. If you memorize the strong ones, then by default all the others are weak. Generally for the weak ones you're doing good if you can get 5% dissociated. There's a huge gap between the weaks and the strongs. The process isn't different, but the extent to which it occurs is different. This next reaction, which is dissociation of magnesium hydroxide, that's an exactly parallel kind of formula to the calcium hydroxide. And the dissociation happens exactly the same way. Those products look identical, correct? But what's different is this magnesium hydroxide is considered a two-way reaction. Careful with your arrow there. Two-way arrow means only partial dissociation. And if we're putting magnesium hydroxide particles into the water, a few of them will be in dissociated form, but there'll be others that are just kind of bobbing around intact. And a few of these will break apart, and a few of these that have broken apart, this is what the reverse arrow is. Every now and then, as magnesium bumps into hydroxide in that solution, they revert back to the neutral form. So it really is a two-way reaction. Some are breaking apart, some are dissociating, and others are recombining. Constantly, both are happening at the same time. And therefore, you never get to the point where they're all dissociated together. You never get to the point of 100%.
So it happens with weak bases.
Weak bases.
Bases to,
If you memorize the strong bases, then all the other metal hydroxides are weak bases.
What about the first and second one?
Those aren't bases at all. These are not metal hydroxides. So that doesn't apply to them.
Okay. So will they, if they're not metal hydroxides, will they always be 100%?
Yes. It's only the bases that you have to be careful with here.
Okay.
If you're dissociating a metal hydroxide, then you need to think carefully about the arrow. Do you see how these two are parallel? The difference is a difference in strengths. The weak ones just aren't going to go apart completely. And that's reflected in the way that you write the reaction arrows.
so if it's not a strong base, you always write your arrows like that.
If it's a base, but not strong, then yes. Yeah, these are not bases at all, so we don't even think about one or two. It's just going to be one way. Question about writing these dissociations. Make sure you memorize who your strong bases are.
Can we finish the characteristics? So involves ions, compounds dissolved in water, water dissolvent on which...
The only change is separation of ions. And I didn't talk about it, and I guess I should have, but these are always going to be single-step reactions. For example, this aluminum has 3 nitrates on it. It didn't lose one nitrate and then another and then another. All 3 nitrates pop off simultaneously. And so that's written as a single reaction. When we get to ionization, it won't be that way. But dissociations are always single-step. Question about dissociation. Ionization. This is going to be covalent compounds, but in particular, acids. The vast majority of ionization reactions are acid ionization. There are a few that are bases, and these are ammonia-type bases. We'll see what their reactions look like in a minute, but they're a little bit different structurally than your metal hydroxides, and so it comes under ionization rather than dissociation. The primary difference here between ionization and dissociation is water is reactant and solvent. With dissociation, water was just a solvent, and you never saw water anywhere in that balanced equation, correct? Unless you count the little AQ labels. But on the dissociations, we didn't have plus water anywhere. With ionization, you do. Water really is a reactant. And so it has to be written as plus water. This is a constant for ionization. Remember when we did combustion, and the definition was plus O2 forming CO2 in water, and that was automatic for combustion? Plus water is automatic for ionization. You have to write water as a true reactant. The only thing that changes in this is transfer of a single H plus. I guess I'll put this out parenthetically. From the acid particle to what we consider as the base particle. No matter how big your molecules are, the only thing that happens structurally is you move an H plus from one formula to another. Nothing else occurs. Sometimes these are multiple steps. We'll do a few examples of that. Products, depending upon whether you've got an acid or base ionization, you'll form either hydronium or hydroxide. One of those is always going to be your product. Acids produce hydronium, bases produce hydroxide. So looking at this first example, where we start with HCl, hydrogen at the front tells you you're dealing with an acid. That's one of the notations to help you identify acids. And so what's going to happen in this reaction is going to split into H plus and Cl minus. And this hydrogen part goes from the HCl to the water. So HCl losing the positive hydrogen, all that's left is Cl negative, but water gaining an H plus. H2O becomes H3O positive. HCl is an acid, therefore produces hydronium. And whatever this remnant ion happens to be, that's your other product. But again, no matter how big of a molecule that acid may be, all you're doing is stripping off the hydrogen. So the rest of that goes through intact. And sometimes that can give you a rather large anion. But it's not hard to predict because all you do is pull off the 1H plus and that's your product. So for HNO3, H plus nitrate's a polyatomic negative. Balanced chemical equation for ionization of HNO3. Are you okay looking at that and knowing that that's an acid? The word ionization tells you you have to add water. The fact that this is an acid tells you that you have to produce hydronium. And as far as moving this hydrogen around, the hydrogen always goes away from the acid. So this hydrogen leaves the acid and goes on to the water. So NO3 negative would be your other product. HNO3, hydrogen, nitrogen, oxygen, all of those are nonmetals. That is perfectly covalent bonding. There really are no charges when you start. Now, I wrote the little plus and I wrote the little minus. I erased them out just now because you don't really have those charges when you start. That is the way it tends to split. But you don't have pre-existing charges like you did on dissociation. They're formed, the charges are formed at the moment it hits water and when that hydrogen leaves. Your products are always charged. Just like with dissociation, products are always charged. So be sure you show those charges. Go ahead and do the next two.
Are those products on the other side?
Yes. Whoops. Yes.
That's okay, I got it.
Yeah. I'll put it back up here. What I was leaving out for the moment was the arrow, because we have to do the same kind of strong and weak thing with these. HNO3 is a strong acid, and therefore it's a one-way arrow, but there's some acids that are weak, and we get the two-way arrow.
Oh.
All right, and I'll list them up here in a moment. So for now, go ahead and do these next two. Don't worry about the arrow just yet, but go ahead and get your formulas written out there. What I've listed up here is your strong acids. There's 7 of them. Those acids give you 100% ionization. Meaning those 7 acids get one-way arrows in their reactions. All other acids, by default, will be two-way. So hopefully when you were writing out formulas, you got this. Is that what you got material-wise? Go ahead.
How do you know if it's going to be an acid or base reaction before you write?
Well, by I guess the notation of the compound. If you see hydrogen at the front of the formula, that tells you it's an acid. And on the dissociations we just did, they were all metal hydroxides. And so that would kind of tip you off to that. Now, as far as base ionization, we'll get to that in a few minutes. The compound, your starting material will be written differently so that it does not have hydrogen at the front. And that way it will not mislead you into thinking it's an acid. But yeah, we'll have a couple of those. And if that doesn't, in a few minutes, if that doesn't take care of it, ask again. Are you okay with that materially for HBr and HF? What kind of arrow does HBr get? And HF? Double. Okay. HBr is a strong acid. Every single molecule of HBr that you put in the water is going to ionize. There'll be absolutely 0 HBRs that remain intact. But HF is not like that. HF doesn't have the ability to ionize completely. And if you put 100 HFs in water, you're doing good if you can get 5 of those 100 to ionize at any given time, which is not much. And even those revert back, hence the two-way arrow. Knowing what kind of arrow goes in there comes down to memorization. But you see that writing out the plus water and predicting the products, you don't even have to think about strong or weak to predict your products. Because all acids do the same thing. Strong or weak only shows up in the arrows.
Do you have a good way to memorize that, or to remember that, or is it just actually memorize it?
For these?
Yeah.
You need to memorize these 7 formulas. Is that what you mean?
I meant,
I'm sorry.
Like, do you have an easy way to remember those? Like,
Oh, like a little mnemonic thing?
Yeah.
No.
okay.
No. Sorry. If you invent one, let me
Please
know.
explain what is ionization,
For
just in general.
the definition,
Yeah, like what happens.
what happens is that, I erased it. What happens in ionization is transfer of a hydrogen.
Yeah,
And that should be your definition of it.
that's,
Okay. All right,
So any, for weak acids, is it anything that's not that?
yes. Any acid that is not one of these 7. And the ways you identify acid, notation-wise, are either hydrogen at the front or a COOH group. If you see either one of those, then that's screaming acid to you. Go ahead and write the ionizations for these 2. Because it's ionization, it has to be plus water. Because this is an acid, it has to form hydrogen. And when this hydrogen comes loose, whatever happens to be left, that's your other product, which in this case, that's C2H3O2. C2H3O2 with what charge? -1. Good. Because this that you're starting with is neutral. So if the hydrogen is +1, this thing has to be negative. And that's your reaction. What kind of arrow? 2A. Question up there. All right, now the other one is just like it. These are both actually acetic acid. These are both the same compound. It's just written in a different form, which makes the reaction look a little different, I guess. But it's really just a difference in how you write the anion. One is as good as the other. But acetic acid is weak and therefore 2A. Question?
Why would we take the H from the very right instead of the H and H3?
The way that these are the same compound, and you've got one hydrogen here that's written at the front, and these 3 others that are not. That's the one at the front is to tell you that that's the one hydrogen that's reactive. So this one comes loose, but the other 3 are very firmly